All right, guys, this is Mr. Hayden. This is Earth Science Week 14. The reason why I'm doing a clean recording and just posting it to the YouTube channel is that we had our ninth graders come in today, and we're doing some PE testing. And so we had a few hours of time, which happens to be during these sessions that the testing took place. So I don't get in the way of that. I just wanted to do a quick recording and post it to you. And just remember a few things that we need to talk about before the end of the semester. We have about 6 weeks left of school, so again, if your grade is at a grade that you're not really happy with, you want to make sure that we bring those up. Want to make sure that your grade is where you think it should be, and so let's go ahead and do so. Your science notebook is actually going to be due starting May 11th all the way to May 22nd. And say you do come on the week of May 11th, so I think it'd be like the 14th or something for May. For this class, if you decide you wanted to come in just during the live session and we grade it. Once I grade it, it is graded. It is not due again. You can continue to work on your science notebook to make sure you're prepared for the final. But once it's graded, it is a done, completed, turned in assignment. Also, please make sure that the questions are your own and from your own mind, and you do not plagiarize. We've had some people doing some plagiarizing, unfortunately, and receiving some zeros on tests, and there's really absolutely no reason for that because of the fact that, if you don't know it, just leave it blank. If you do know it, then put the information that you know in. You will receive a 0 on the test. So specifically on the final, if you choose to plagiarize on the final, you will get a 0 on it. And if you did it before, you will get a F in the class. So let's just not do it. Let's stay away from it, and let's stay positive, and let's make sure we understand everything before we take the test. Now, we're going to talk about the essential question. Okay, so what is the cycle of our sun? Okay, not a star, not a star specifically, but like an actual our sun that we have in our solar system. Because every single star, which our sun is one, has a specific life based upon various circumstances. We're going to kind of hit on those. One of them is its size and made of and things like that, how hot it burns, things, other parts of that nature. But we want to discuss from the beginning and to the end the life cycle of, say, our sun. So to measure, we're going to go over distance first. We're going to talk about the measuring distance in space. You can't really talk about like a year or a foot or a meter. It's too small. We need something to actually fill the size of space. So we call it a light year. A light year is the distance light travels in 1 year. A light year is equal to a little under 6 trillion miles. So when you say, well, it's 5 light years away, well, that'd be 30 trillion miles away. That's substantial. And we have to do that. And the reason why we do have to talk in that case is because, our distances, say from here to Mars, takes a month. The distance here to Jupiter, takes a long period of time. It takes, upwards of 20, 30 years to get from our point to the outer parts of the solar system and whatnot in a certain amount of time. So we really got to talk when we discuss distances being in a large number of units. Okay? So we have right here another solar system right here, which is Proxima Centauri. Is the closest star to our solar system. It is about 4 light years away. So 24 trillion miles away is the closest next star to our solar system. So again, it would take 4 years to go there going at the speed of light, which right now we cannot do. So again, even traveling at a speed that we can't even reach, it would take 4 years to get to that location. Traveling as fast as an average spaceship, it would take between 70 and 100,000 years to get there. That is crazy. That is a long amount of time, basically, to send out. So, give an example. If, 100,000 years ago, there wasn't even people on this planet, or at least to the extent of what we call people. So it's amazing on how long it would take to get somewhere. So here's a few different names of the star sizes. We have the supergiant, which is obviously really big. We have a giant one, and then it starts to make its way down. It starts to make its way down from a giant, medium-sized, white dwarf, neutron star, all the way through. Our sun is actually a medium-sized star, which is good because it's not so big it will collapse on itself, and we'll see later can cause other issues. It's also not small, and it's so small it doesn't give off enough energy to allow for life and things on the planet. So in comparison with our sun with a white dwarf and a neutron star, our sun is going to be much larger than a white dwarf, and then also a neutron star, it's going to be very small, almost the size of like a planet. But it's in comparison to each other, obviously. So when you look at the different stars right there, you'll see different colors. What they do is they can get various types of radiation and readings and whatnot for the surface temperature of the sun. Anything that is blue, it means it's really, really hot. If it's it's considered cooler to the extent of sun's being cooler, the coldest is going to be in red. So example, this one right here is going to be much colder than this one right here in comparison from star to star. So when we look at absolute and apparent magnitudes, we're going to look at two different things. Absolute magnitude is how much light is actually given off by the star. How much radiation, or how much, not even just light in the general form of what you can see, but also what wavelengths are given off, or how much wavelengths are given off. Apparent magnitude is how bright the star appears due to how close it is. So a star can be really, can have a very low absolute magnitude, so it doesn't give off much light, but it's very close to us, so we'll have an apparent magnitude of it being brighter. On the opposite thing, you can actually have a really, really, really bright, a really energized star that gives off a whole bunch of light and is really, it has a lot of energy in it, but it's so far away that it looks very dim to us, so it would just appear to have a lower apparent magnitude. So two astronomers discovered a relationship between these absolute magnitude, the real brightness of a star, and its surface temperature. And they plotted the data, so these two people from Denmark and the US, way back in the day. And they've shown that stars seem to be naturally grouped together based upon what they are. So example, there's stars right in the middle here. There's various stars that, they seem to clump. You see there's nothing in this location. So there is a direct relationship between its absolute magnitude and its temperature on its surface. So here's a kind of a better picture to show you. Here's obviously the larger planets at the very top over here, and these are all supergiants, very big. We have other stars. These are all named based upon when they were found and be able to name them and whatnot all the way through. We also have some white dwarfs, so very small type planets here. They discovered that stars grouped by the type and during their lifetime would move from a place on the graph to another. As the sun ages, it will move to a giant star to a giant star to a white dwarf, depending on how much energy it gives off in its life cycle. So speaking of life cycle, the life cycle of a star is when a star forms, it begins its life and starts to actually basically fuel this type of radiation and push outward. So a star is a lifetime similar to a battery, and it cannot be recharged. When the battery runs out, it's finished. Our sun will run out of energy, and it will be finished too eventually. But this will happen in about 5 billion years. So the billions of years from now, it'll probably run out, and by that time, we'll have the capabilities to probably move to a different star if we need it. Main sequence star. So here's the life cycle of a massive star. You can see right here that it's a cycle. Okay, so it's going to basically start by star-forming nebula. It's going to create a sun, create a star. The star will eventually become a red supergiant, and then eventually it will explode or have an explosive outburst, become a supernova. And then based on its size, we have a couple things. It'll either become a black hole, it'll become a neutron star or a pulsar star, or it'll just become interstellar medium or dust to allow for it to be re-brought back in and created into a new star eventually. So life of a star here, again, is just another way of looking at it. Average star, I believe that we're right about here. Okay, so our sun will go in this location. This is a massive star or a large one itself. The bigger the star, obviously explodes and then becomes a black hole or a neutron star, which is bad, and I'll go over that in a second. The average star makes its way this way, it becomes a star. It will then start to expand, become a red giant, which has not happened to us yet, become a planetary nebula, and then eventually it will become a white dwarf, and that will be our sun eventually. A massive star will then become a red supergiant, become a supernova, explode, and one of two things will occur. It will become a neutron star, or it will become a black hole. Either way, it's bad. Black holes is an area where there's so much, pressure and whatnot, and coldness, and gravity to basically crush everything inside of it. But a neutron star can also be not as good as well. It basically shoots like two sides of a gun out these neutrons that completely can destroy, say, planets or whatnot in its way. So both of those actually take place. Remember, life cycle of the star based upon its size. So a life cycle of our sun, we're here right now. So this is us. Eventually, after 5 million years, it will run out and it will become this. Once this giant stage happens, they still actually just expand. It will engulf most of the planets around the inner part of the solar system, but we don't have to worry about that because it's going to be 5 billion years. So a galaxy is a large group of stars bound together by gravity. So we live in the Milky Way galaxy. We're just one solar system part of that. But there's 3 different types of galaxies that we see. One is a spiral, one's irregular, and one is elliptical. So let's go ahead and look at a few of those. So here's some pictures from the Hubble Space Telescope. You can see the spiral galaxies. You can see there's a center, and it kind of spirals outward this way. It's pretty straightforward there. And we continue. We notice that individual stars in the picture here, you can see them, but they're not part of the galaxy in the picture, but they are part of our Milky Way galaxy. So they're kind of between us and that location. So why are they in the picture? Well, it gives you the idea there that if you look out a window with wood trim, it is hard to get a view without them in the way. These stars are in our view as they're looking out into the galaxy, which means that they're in between us and this the next solar system that we can get pictures of. Now, elliptical galaxies, again, we don't get to really see them very well, but obviously the ellipse is like this. Not so much here with spiraling outwards. Spiraling outwards like this, sorry about that. So this is more of the spiral one. Elliptical is this way. You can see we don't have very good pictures of them. Irregular galaxies are kind of just all over the place. There's no set shape, and they're kind of, I think they're considered new galaxies, and they're starting to actually start to spin, and they haven't got its way to actually spinning correctly. Our galaxy is a spiral galaxy, is what we think, because if you look, we're here, but really we have no way to kind of look at it. So we don't really know. We're just guessing. This is not a real picture of our galaxy, just one that looks like what we think the galaxy looks like. So here's what the top view looks like here. You can see that you can see the spiral moving outwards. Here's our sun. Here's all the various places around it. There's a center to it. This is what it looks like on the side. There's a nucleus in the middle. And in our sun, you can see there's a massive amount of energy in the middle of our galaxy. So our view of the Milky Way galaxy is this. You can see that you can see all these different spots. It's not dust. Those are actually stars and planets and everything else out there. So there you go. The Milky Way galaxy is about 200 billion stars just within our galaxy. And remember, there's other millions of galaxies out there. So there's everywhere. Now here's some just really cool pictures to show you. There's a Horsehead Nebula. You can see the way it looks here. Let's call this one a Witch Head Nebula. You can see why. It looks like a witch, and there's the mouth. Right here is the reveal of various different names because of what they look like. These are nebulas, so again, these are where new stars are going to actually start to form. North American Nebula, there's the Cat's Eye, the Ring Nebula, and then the Ant Nebula. All these are various nebulas where new galaxies are starting to form around a central sun or near point. So the current estimate of the age of the universe is about 13.7 billion years. The solar system is 4.6 billion years old. So the solar system is not the same age as the entire galaxy because of the fact that it started forming with the nebulas after the galaxy took place. So if there's any questions, make sure you email them to me. Make sure you answer the essential question, put them in your own words from start to finish, and put those in the comments area in the box for week 14 to get credit. And I hope that you have a good rest of your day. And if you are in 9th grade and you did not come to the PE testing today, try to call Ms. Demmer or email Ms. Demmer or K-Mailer to figure out when there's a good time for you to make it out. Thank you. Bye.